Welcome to springlib.
There's a cliff on top of an ocean, and a projectile was launched a certain angle, theta, above the horizontal at an initial velocity. What we want to do is we want to figure out the time at which the projectile reaches its maximum height. So let's do that first. That's the first goal here today. So we're going to go ahead and use some powerful kinematic equations here. First one that comes to mind is this one here. The Vy final equals the Vy initial plus any changes in the acceleration multiplied by time. So the vertical velocity at a maximum height is momentarily zero, which is true. This is going to be zero at the height. So we're going to set that right away equal to zero. And then this Vy initial, this guy right here, this guy is the initial sine theta. V initial sine theta. And of course, the acceleration, though, is pointing downward. Because of that, we want to use a minus g for the acceleration, minus g, plugging in minus g for the a sub y, multiplied by t. And we can go ahead and solve this now for t. T being equal to the v initial sine theta divided by g. And that's our time of flight. So we'll go ahead and we're going to box this in, leave it to the side for now, and we'll move on. All right, so we want to find the maximum height the maximum height essentially for the object. Now keep in mind we already are a height h off the ground, so that's something we need to keep in mind about the problem. That has already affected our height quite a bit. So let's be sure we keep that in mind as we look for h max. So we're going to go ahead and use this equation here, another lovely kinematic equation. Lovely. And just to make this a little more clear, acceleration in the y direction times t squared. Excellent. All right, so we can go ahead and start plugging in what we know here. So this y final, we're going to define as just the h max. That's that max height that we're looking for. And the y initial, well, that's how high we got up to, or the cliff is originally. So we'll just define that as h, as described in the problem. And then we're going to go ahead and plug in this Vy initial, which ends up just being Vi sine theta, and we multiply it by t. But remember, t is now this, so we want to plug that in for t. Vi sine theta over g. And at this point, we're going to need to plug in a minus for the g, because for the acceleration, we need to have a minus g. So I'm going to actually put that down right here. That's continuing on right here. So minus 1/2 g, and then times t squared. Remember, t is this Vi sine theta over g. V initial sine theta over g. And do not forget the t is squared here. So we have to make sure to include that here and square this whole thing. All right, so I'm going to move over to here now. Gives me some more space. Moving down here. And we're just going to keep cleaning up this a little bit. So we have our h max. That's equal to h plus the initial sine theta times, keep in mind you have all this stuff together here, so you can just square those guys, put them together, Vi squared times sine theta squared. And the g is going to tag along on the bottom there. And we have the minus. Remember, this stuff is just continuing on from where this would be right here. So minus 1/2. And it would be 9.8, but we're just going to leave it in the terms of g for now. 1/2 g. And then go ahead and distribute that square and everything here. So Vi squared sine theta squared course, the g is going to get squared as well. G squared. All right, and we can go ahead and clean this up a little bit more and make this look a little bit nicer. So we have h max equal to h plus, and we have all this stuff grouped together here. We have a v I squared sine squared theta divided by 2g. And that right there is our expression that describes the height.